Thank you. And thank you all for having me here. It's really nice to be back. My general relativity professor is here in the front row, which is great. And I have to. So I was an undergrad here and had a very positive experience. And I worked with John Wheeler on my junior paper and my senior thesis, actually on gravitational waves and black holes. But slightly different from this, that was trying to make black holes out of colliding gravitational waves, which turns out is probably not relevant to our universe. But I'll be talking about other gravitational waves today. OK, so I'm going to try to give you an overview of 170817. There's a lot to talk about, so I've kind of picked a few things that I'm particularly fond of. But this is the sort of topic that we could spend weeks on. It's an amazing event, just as one event. So I'll try to give you some sense of that as we go along. So first, let's see. OK, so this is my highest level overview. This is the very basic overview, which is, OK, the big deal here is that for the very first time, we're detecting gravitational waves, and we're seeing light from an object simultaneously. And that's never happened before. And that immediately lets us do all sorts of new science. The most obvious is you can test whether the gravitational waves go at the speed of light. We've learned about the gold in the universe. We learn about star formation and evolution. And my favorite, we learn about the scale of the universe. And all of this is possible because of this combination. And I'll talk about all that in a lot more detail. So here's a slightly more zoomed in version. So this is the first binary neutron star. There are a lot of firsts here. And each of these is a major development. First binary neutron star detected in gravitational waves. So that alone would have been very exciting as far as LIGO is concerned. The first joint gravitational wave in GRB detection. That's also a major development that would, both from the gravitational wave side and from the GRB side. It's the first time we have an optical counterpart and basically the entire spectrum. And of course, that's also incredibly exciting and is a major development. So each of these is a major development. And all of these happen simultaneously. And there's a lot of other things we get to do. OK, so that's my highest level overview. And now I'm going to go into kind of how this is all played out in practice. And it all starts August 17th. It was sort of early morning in Chicago. I wasn't in Chicago. I'll get to that in a bit. And we detected gravitational waves. And we've been doing, I must say, by the point that this came through, we'd had a number of detections, some of which have been announced. And we were already pretty tired. And the detector was about to turn off. It was supposed to be on for another week or so. And to be honest, we didn't really need this or want this at that particular moment. But here's what we got. We got a chirp. And so, so this is a time frequency pause. It's just time frequency. And the kind of, how bright it is here is the amplitude, sort of some normalized. We have some way of, we take a little bin and we ask how much sort of energy is there in that bin. And this track is sort of, this is what we've been looking for within LIGO. LIGO was essentially built to find binary neutron stars. And the telltale signature would be a track like this. And so anyone within the collaboration, if you show them this track, they get very excited. I mean, this is what we've been doing. For over a decade, we've been dreaming about seeing something like this. And so this came in at Hanford. And there was a trigger. But it was a single detector trigger. And that's a little odd. So I'll get into that for a second. But this was a very loud track. So the fact that you can just see this by eye already tells you this is an extremely unusual event. The sort of average events, I would show you the sort of events we prepared for. On this picture, you wouldn't really be able to see anything. Maybe if you squinted and stacked a bunch of things, you might be able to see it. But you shouldn't be able to just trace it out.
So in practice, you get data of this quality more or less in real time? You get a picture like this? Or
yeah, this comes very quickly. Yeah, we have an automated thing where it triggers and it uploads to a site, and we get to just look at the site. So, and we've had a lot of practice with our other events, so we're pretty good at that now. And we all get on to Telecon and we discuss. And so, so very quickly, everyone was on a Telecon saying, OK, this is this beautiful track, but it wasn't at Livingston, so there was no automated alert. So some people got messages, but it wasn't sent out to everyone, and it wasn't sent out to our EM partners. And the reason for that is that Hanford and Livingston are very close in polarization. They're about as closely aligned as you can have on the globe. I mean, they're on different parts of the US, so just because of the curvature of the Earth, they're not perfectly aligned. But they're very close. And the idea for that is, so then you're quite confident if you see a signal in one, you have to see a pretty similar signal in the other. It's very hard for them to be very different. And so if you get a loud signal like this in Hanford, you'd better see something in Livingston. Otherwise, you have a problem. It's not real. So the question is, what happened? And this is what happened. And this was actually first realized by Reed ESIC, who's a postdoc at Chicago. And he pulled up the Livingston version of this. Omega scan is what we call it. And you can see that there's a problem. And this was all vetoed because there's this huge glitch in the data. Okay? And so, it makes, this happens once every hour or two. You get just a glitch. We don't know what it is. Something in the instrument. I haven't given you the whole background about what gravitational waves are, how amazing LIGO is. LIGO as an instrument is phenomenal. It's beyond, even to this day, I can't believe it works at the level, at the sensitivity, 1.10 to 22. It's just mind-blowing. But we're not talking about that at all. But given how sensitive it is, stuff happens all the time. And this is one of the things that happens. So there are all these categorizations of glitches. This is a very common glitch. And it's just, we don't know, some micro adjustment in one of the fibers. Or so something happens. And you get a little very distinct glitch. There it is. But what Reed recognized immediately is underneath this glitch is an even more impressive track. That's unmistakable. And that really is, in all our simulations of what we might see, no one had ever produced something that's that loud in one detector. That's extraordinary. So he was probably the first person to realize, we have a real event here. It's a BNS. And you can tell just from the length of the track. OK, so then there's this huge glitch. That's a problem. We have to take out the glitch. We've never really done that before. But since the track is really very visible, we were extremely motivated. So we took out the glitch. So this is, we're just kind of making it up as we go along to some extent at this point. The easiest thing to do and what we did at first was we just kind of gated it. We just applied, first we actually did a notched. We just notched out that part of the data. But that then rings off the edges. That turns out not to be a good approach. So then we kind of had a smoother notch. And then eventually we actually fit the glitch and just took it out that way. It's very loud, but it's a very regular glitch. And you can do that. And there's a lot of stuff behind here. But just, here we are. We have this incredibly exciting event. But it's not your vanilla event. So we have to do something. So on the fly, we're adjusting our analysis pipelines and redoing it, and quickly on a time scale of tens of minutes, because we really want to get this out as soon as possible. So I think we feel pretty good about how much we managed to do on a very short time scale. OK, and this is it without the glitch. And that looks pretty good, right? So at this point, you can see there's this unbelievably clean track. It's beautiful. So the SNR in just this track, in this one detector, it's louder than the combined SNR of 150914, the first event, which was that incredibly beautiful, loud event. We were never going to have an experience like that again, because that was our first one ever, and it was so loud and beautiful and perfect. And here, in one detector, we have something that's even louder, and in some ways more beautiful and even more perfect. It's crazy. OK, so at this point, we're pretty excited.
What factor was the sensitivity of LIGO improved to make this new thing?
Yes. Yes. So not only so it's not that much more sensitive than 01. You know, maybe we went from 60, 65 to 80 megaparsecs on a good day. You know, it varies. Our sensitivity varies. So it was not a dramatic improvement in sensitivity. So in 01, in the 2015 version, we easily would have seen this. And in fact, it's so loud that in S6, in the version in 2010, initial LIGO, you probably could have seen it. I mean, it's marginal, but it's in principle detectable.
What year is that?
2010.
You could have seen this in the 2010.
Yeah. Which is interesting because that tells you that the 2010, you know, the rates, when you do the rates, you know, this kind of gets relevant as well. And so it gets a little more complicated. But yes, this is unbelievably loud. So, okay. So it's really loud. Yes? It's 32. So, and I'll get more about that. So, you know, here's this insanely loud event in Hanford and Livingston. The next question is, what about Virgo? Okay? So this is Virgo. And there's nothing there. So, you know, so that could make you nervous.
Color scale the same?
Yeah, the color scale's the same. So, you know, that's not very impressive, and it's really extraordinarily loud. Okay, so the first thing you're probably you know, going to ask is, you know, it can't be nothing. It's so loud. There must be something wrong, right? Okay, and then, you know, if you're in the LIGO collaboration, your assumption is, you know, well, maybe Virgo's not working because Virgo has had lots of issues. But just a few days before this detection, just a few days before, we'd had another detection, and that so happened to be at a period where all three detectors were operating. And you know, it has to be said, that only started in like August 1st. This is August 25th, August 17th. And August 14th, we had another event. We'd only been on for a couple of weeks. And that event triggered all three. Well, it didn't trigger Virgo, but we could go back and extract Virgo. And so we had an announcement, which some of you may have heard. This was very, I mean, there's a whole backstory on this, which but we made this announcement, which, you know, rumors had leaked. And so we had an announcement, and a lot of people thought this is our big announcement. And the announcement was simply, oh, we got another, you know, binary black hole system, kind of like the first one. Not that loud, nothing really new about it, just a boring black hole. And everyone was like, why did you have the, you know, there were all these rumors. People had actually, you know, gone up early to hear the announcement, and there was nothing, basically. But the reason we did that announcement was because this was the first time we'd had a triple, LIGO and Virgo. And OK, Virgo, it's not incredibly impressive. But there is some signal to noise. There is that blob. And you get to integrate across this. It tells us Virgo is working. Okay, and that's very important to us. So Virgo is working. Virgo did not detect this event, 170817. So that could make you, you know, extremely nervous. So here's the combined SNR. The Virgo SNR at best, if you take kind of your best thing, is like 2. But that, you know, we would never call that, you know, any sort of independent detection in any way. So basically, you know, that's the situation we're in. And so at first, this really, you know, this made us very uncomfortable. There's only one, you know, assuming there's nothing nefarious or we're really missing something about the detectors, there's only one explanation for how this could work. And that has to do with the antenna response functions. So I'm just going to show you how this kind of plays out. So this is a picture of the beam pattern. So the way to think about this is the detectors are fixed to the surface of the Earth. Okay? And so the sensitivity of the detector is related to the shape of your detector. So for example, you know, if this is my Hanford detector, if I have a source directly above the detector, I'm very sensitive to it. And if I have a source right at 45 degrees. If you think about it, so if that's my detector and I'm out here at 45 degrees, I'm not sensitive at all. Symmetry arguments can kind of tell you that. So the detectors have blind spots, are really sort of deaf spots in the way we think about it, where they just have no sensitivity at all. Okay, and there are a number of these, and then there are places where you're more sensitive, less sensitive. Okay, so this is the map for the sensitivity, and here are the spots where there's no sensitivity for Hanford.
As you point out, the sensitivity also depends on the polarization. Even if it's straight overhead, there would be a polarization.
Yes, that's right. So this is kind of a sky averaged.
How do you allow for that in this
Yeah, so for this, I'm kind of averaging over all possible polarizations. But that's right. So if you had directly overhead and face on, it's very loud. If it's edge on, then your sensitivity goes down. And depending on the actual angle, you can mess with that. That's exactly right. So I've just averaged over that. And it's a factor of a few, depending, if you take the best to the worst. Right. Are there any other questions about this diagram? So, OK. So for now, just ignore these other contours. So this is what we get for Hanford. And now I'll just show you Livingston. It's pretty similar because, as I argued before, the alignment is very similar. There's a little shift, and that shift is very important because that helps us do the sky localization. We use that. We use timing, and then we use the very slight difference in the response, which produces a slight difference in the signal to noise in our detectors to infer sky positions. And so when you use those two, and this very high SNR, the high SNR helps, you get these blue contours as our localization. OK. Now let me show you Virgo. OK. So here's the story. And you could say, this can worry that there's something circular here, but it's all consistent. And I think the main point in the end is that we now have an astrophysical calibration that tells us this whole story makes sense, which is something I never thought would happen in gravitational waves. But OK, for what we have so far, what you notice for Virgo is that there is, this is a spot where you have very, very low sensitivity. And if you're close to this spot, then Virgo shouldn't see anything. Even if it's insanely loud, Virgo doesn't have, its sensitivity already to start with is less by a factor of, maybe 3 or 4. Plus, if you happen to be near a, low spot in the Virgo sensitivity, the whole picture fits together. Another way to say that is because Virgo had nothing, it's kind of has to be close to one of these. And then when you fold in the two LIGOs, you end up with this little white region up here. And I'll talk more about that. Okay. But this is a long-winded way to say, have no fear. It's OK that Virgo didn't see anything. Actually, it's very helpful. And so Virgo's non-detection was very important to our detection. Yeah.
So you're parsing it out for the top, but thinking out, then you consistently take into account what the sky coverage is going to be in a star.
That's right.
So you're saying, sorry, just to reiterate, the contours are the localization before you take into account the coverage of Virgo. Is that right?
Yeah, the blue ones are without Virgo. It's just with the two. This tiny little white one. I'll have a better picture of this in a little bit.
And that's when you add the sky coverage.
That's right. That's right.
And what's the factor?
It goes from something like 190 to 30.
And just one more question.
Yeah.
If it wasn't near the blind spot of Virgo, how much would Virgo have helped that much?
Yeah. So if it had been somewhere around here, then would be more constrained. You can think of it as this is a smaller spot than these for equivalent SNR. So the fact that it's in the blind spot really does help you with. So which is an interesting thing in general about gravitational waves is that our ability to localize depends on where the source is on the sky and also on the polarization and inclination. Like it depends on a lot of other things. So it's not like an EM telescope where it depends on the atmosphere above the telescope and the clouds and stuff. I mean, for us, it really is primarily dependent on properties of, out there, of the sources themselves.
30 square, we should not keep 30 square degrees as sort of now the fiducial number.
Oh, no. This is, so one thing I'm going to have to, and I'll reiterate this a few times over the talk, this is a very unusual event. You should not now normalize to this event and expect from, for the future, this is what we're going to be getting for our gravitational wave sources. Yeah, that's right. So this one, and so in some case, anyway, we can talk about, so you do get lucky. And so I've been writing a series of papers specifically about being lucky, golden events, where, and pointing out things such as if you happen to be in one of these spots, you get much better localization. And so I'd gotten very excited because there's some fraction of events where you do end up right there, right in the perfect. Or, for example, we do timing. And if your time difference, your arrival difference, our main way of getting localization is through timing. And if you think about how that works, if you have two detectors and your signal arrives at the same time at both detectors, then you're on the sky equally centered between the detectors, right? Okay. If your signal is the actual light travel time, then you've got a unique localization. It's along the axis joining the detectors. And so some fraction of the time, just through timing, you get a perfect localization. And you can quantify that. And that's extremely useful because if you get perfect localization, then you can identify a unique host galaxy. You don't even need a counterpart. You can just identify, here's where it came from, here's its all that. So that's quite interesting. That's not what we're talking about here, but that's something I am excited about. OK. All right. So we detected the gravitational waves. So this came, pretty quickly. Let me just go back. So we sent out a circular, quite quickly afterwards. We did the glitch, we did all this stuff, and within something like 40 minutes, I think that I forget, there's a notice in a circular. Within 30 minutes, we had alerted people. First BNS ever, and it was not a clean detection. Sort of like 150914, our first BBH. That was also not clean. It was before we were in science mode. But we managed to get that out reasonably quickly. And this one we got out very quickly. Okay. We were excited about it. OK. So I'm just going to show you this video of here. It's good to just see the waveforms. So here are the waveforms of kind of the most prominent BBHs we have so far. This is the very first one. And there are a few things. One is you notice where you merge in time. So the time here, 0, is when it comes in band. And so if you merge fairly quickly, that means you're merging at lower frequency, which means you're more massive. OK, so we've had some more massive ones. 15, 12, 26 is kind of a lighter system. So it stays in band longer. The amplitude here gives you some sense of the SNR. So this one was really very, very loud. This one integrated up. It's pretty loud. So this is where we were before. Okay, and I'm going to now show you 170817. And it's a little different. And I should say, actually, this is made by Ben Farr, who was a postdoc and is now faculty at Oregon. And he this gives you a sense. Now, this is actually a really long movie. But I think I'm going to let it play. Now, unfortunately, the sound system here is going through the projector. You don't really get it. So sound is playing. And if you play this, with a half-decent system, it's amazing. Right now, there's this rumble. And it's really cool. So yeah. So if I highly recommend going home and headphones, or if you have a good stereo system, I'll send you the movie. It's really worth playing. It's impressive. And this is close to the end. OK. So that's the event. It went this whole time in band. Okay. It's totally different from anything we've had before. Thousands of cycles. All right. OK. So. Okay. Yes. Yeah. OK. That gets a little tricky. Exactly. What? So we get to. we do a best fit waveform, and then we can ask, on that waveform, given the noise, how much signal are we integrating as a function of time? And it starts out pretty slow. So there's not that much signal above, I forget, 26 hertz, or we have some fiducial lower limit where we start integrating. But there's some signal. I mean, if I just gave you the first 10 seconds and asked, is there anything there, you wouldn't know. But if you have a prior that it's consistent with the end part, then you do get something. I think another way to say that is if you cut out any few seconds on this and asked, is there anything there, we wouldn't know for sure. But integrating across the whole time, we get this extremely loud signal. But that's the way we do our analysis across the whole band. OK. Yeah?
For all these events, you have two detectors online?
Pardon?
For all these events, you have two detectors online?
Yeah. So for these, Virgo was not operating at all. So we only had Hanford and Livingston. And there's a big discussion, will we ever even announce a single detector trigger? And that's another,
Why not? If you saw only the Livingston thing, let's say Hanford was off
yes.
1708,
Yeah.
would you announce it?
So that would have given us a real crisis. Because there's we're conservative as a collaboration. We really want to be confident in our detections, our announcements. So that's part of the reason we have two and why they're aligned. It's kind of boneheaded to align your two detectors because you don't get any polarization information. You do worse at sky local. I mean, everything, it doesn't make any sense, except that it gives you real confidence when you do get a detection that it's real. And so with only one, a long track, so for a short track, like for this, if we had had only one, I don't think we would have ever announced it. Because you just worry that there's some sort of glitch that happens. You see it in one detector. Maybe it's once a year, but you don't want to call that a black hole and make some big announcement. So the probability of having two glitches at the exact same time that only happen once in your that gets astronomically low, you're fine. So we really want at least two.
When you have two detectors are indistinguishable from a real signal? Two detectors, one detector has a glitch.
Yes.
Indistinguishable from a real signal?
So indistinguishable is you have statistically.
Using your system.
So what we do have, so that okay, I could give. There's another talk which is very interesting on how we do the detections. So what I can tell you is if I take the signal from, say, Hanford, and I analyze Livingston data that has no signal in it, I find lots of coincident detections. Because there's signals, they're not loud signals, but they're loud enough, but they're not real, they're glitches, that look black hole enough and are consistent with the noise enough that you would call it a detection. And that's how we estimate our background. So, so we try to take out those chance coincidences when we give a number, which is why our threshold is so high. Our signal to noise threshold is 12 for the network. And you could ask, why isn't it like 3 or 5 or something? And it's because of this. We have this background that we don't fully understand, but we can characterize. And we want to be way past that. And the coincidence, double coincidence, is our key tool. So I really don't want to take that away. How?
So in terms of detection power, there's another 50% to go if you have the perfect signal processing.
Oh, a perfect signal process. If
you could detect all the glitches.
If we understood our noise, we would go much, much farther than that.
50%.
It would, no, it would be much more than that. I mean, we're at, at least 8. And if you understood the noise perfectly, maybe you could go to 5. So, OK, it's a factor of 2 plus cubed in volume. I mean, that would be a big difference. But we're nowhere. I mean, it's exponential. Like you go down from our threshold is 12 for the network. If we went down to 8, we're totally swamped. There's nothing there. Yeah. So.
Signal from one and then hit it to the other, but hit it coincidentally, like at the same time channel, right?
Yeah. Yeah, that's right. So we do a full MCMC on the data. The time of the event is one of the parameters, but we do it all simultaneously. You get a lot of matches, even against noise, if you allow it to be anytime. So yeah. Right. So it's and that's so the two detectors is important. That's the moral so far. So I even though I mean I do think that this either of these is so beautiful, like this one especially. It would be really hard to not, publish this. I mean, it's just gorgeous, and we've never seen a glitch that looks anything like this. But given that there was a huge glitch in the middle, if this is really all we had, I would. Anyway, thankfully that's not where we were. Right, that's right. This is unusual. We haven't seen anything like this. So that's why I feel like would be, tempted. I mean, but we do see, glitches that kind of look like this and then come back down, for example. There are glitches that last longer. But, this is a perfect chirping signal. It's perfect. And you can see it by eye. I mean, so that's why, the temptation would be huge in this particular case. But I don't know. I don't know what would have happened. Yeah, I mean, it'd be a lot. But then, well, OK, then we'll get to the next thing. It would have put us in a difficult spot. OK, so from these signals, just to give you a sense of what parameter estimation looks like, you can fit for masses. And so now we're doing the full MCMC. And there's some issues of priors on spins, and I don't want to get into this too much. The point here is that you can fit for the masses, and you end up with the more massive one being somewhere in this range, and the less massive one in this range, which is, roughly speaking, 1.6-ish, 1.5, and 1.2, 1.3. Okay. And you kind of knew that already. I mean, you knew it was going to be low mass, because it had this incredibly long chirp and ended up at high frequency. And here are the masses you end up with, which, needless to say, are quite suggestive of neutron stars. And so we end up making, so here are our final ranges. This is 90% intervals. OK, and again, there's a lot of debate. This is all we know. I'll talk about this more in a little bit. We just get the masses. So we can't say these are neutron stars. We can just say the masses are consistent. But we call them neutron stars anyway in our paper. Yes. So the chirp mass is constrained to I think it's 1.10 to the 4. Okay. But it's redshifted. It's small, but there's and there's peculiar velocities, and there's all this. So the actual intrinsic chirp mass is only known to maybe 10%. Anyway, we can talk about that. It's interesting. And we quote source frame. So we quote a source frame chirp mass, which has too many significant figures as far as I'm concerned, given the fact that we don't know.
But the chirp at the end wouldn't have occurred if it was wide dwarf.
No, that's right. So we know that the masses are real. And the chirp mass is some common. So the chirp mass is that overall scale. It's the one scale we have. It's what gives the shape of that curve. But it's a combination of the masses. And to disentangle the masses gets tricky. We have to use other information. So here's just kind of a visual of this, just to give some sense of where we are. Here are kind of some sample of the known black hole masses. So this is solar mass. The x-axis doesn't mean anything. And it's just here are a bunch of the known ones. And then here are the black hole. These are the 4 announced events. And then this is the LVT event, just to give you a sense of where they are. And here are the known neutron stars masses. OK, I mean, some of them are a little uncertain. But roughly speaking, here's the famous mass gap. And here is where our masses ended up. OK, I'm just trying to argue, if I asked you, is this a black hole or a neutron star, you're going to say neutron star, I hope. But if you ask from just the gravitational waves, do we know whether these are black holes or neutron stars? The answer is no. And this is a very complicated plot. And there's a lot going on behind this, which I don't really want to get into. This is deformability. It's sort of a tidal parameter. And it asks, do we have evidence for structure? If you have neutron stars, they're quite puffy compared to black holes. And you would start to notice that puffiness that start to deform. And that changes the phase evolution of your waveform. And you could hope to measure that in your detection and say, oh, we're starting to deviate from the black hole. And in this plot, 0, 0 is black holes. And these are different equations of state. So these are kind of puffier neutron stars and more compact neutron stars. And what you end up is saying, well, here's our 90% upper limit. We rule out really big neutron stars. But we can't tell whether it's a neutron star or a black hole. Okay. This is something we would love to be able to do and really nail down equation of state. We can't really. This was the best we could do in 2 months after the detection. We're hoping to do a little better. I think a lot of people are going to work on this, but we're not going to nail the equation of state with this event, even though it's an unusual event. Okay. So the rest of the story, so you already know. And this is relevant to the single detector question. Fermi also detected this. And this is what Fermi saw. So here is our beautiful chirp. It's very high signal to noise, it's perfect. Boom, the merger happens at that black line. And then sometime later, there are these excursions. And if you look at it's clear that the Fermi the data kind of goes all over the place. This is not a super high signal to noise detection, but it's a confident detection if you ask the Fermi people. This is the way it works, partly because it's in 2 channels. And then Integral also saw it. So I think there's no question there was something. There was some burst of gamma rays about 1.7 seconds later. Okay. In addition, if you can use the Fermi data to estimate positions, sky locations. If you use just the Fermi data, you get a blob like this. If you do just relative timing between Fermi and Integral, you get this band. So it's 2 detectors, so you get a circle on the sky. And it just so happens, if you then overlay the LIGO map, it fits right inside there, which is suggestive. Everything at least is consistent. So we call this a coincident gamma ray detection. And if you do a very rough estimate of the chance probability of just having a GRB at that part of the sky within 2 seconds, it's some very small number. So we have a GRB. It's a very odd GRB. I'm not going to spend any time on this, but it's orders of magnitude under luminous. And the only reason we know this is because we had the gravitational waves, and then we got a host galaxy, and we know the distance. And OK. Actually, we could have even done this just from the gravitational waves because we have good estimates of distance. So there's something weird about this GRB. Could be opening angle. Could be something else. The inclination angle. We expect it's probably off axis. We don't know. Very interesting. Lots of work to be done there, which I'll skip over. OK. One very easy thing you can do. We did this within an hour and had basically the numbers, which is OK. You have some distance. It's just from the gravitational waves. You're going to measure a distance. I'll talk more about that later. It's about 40 megaparsecs. So the gamma rays arrive within 1.7 seconds of the gravitational waves, which sounds like that's a pretty big delay in terms of speed of light. But it's not a big delay if you think that it's been traveling for 100 million plus years. So that whole time, they still arrive within 1.7 seconds. And so you can just immediately bound the relative speeds of these. And it's within a part in 10 to the 15, they're the same. Okay. You can do it two ways. You can assume the gamma rays were emitted as late as 10 seconds after the gravitational waves and then caught up to be only 1.7 seconds, or that they were emitted at the same time and were delayed by 1.7 seconds, and that gives you your two limits. Okay. So this is, we haven't been able to do this before, and now here we are, many, many, many orders of magnitude constrained. Okay. So all this stuff happened. For what it's worth, I kind of missed all this. I was on a plane. I'd given some lectures in Hong Kong, just summer lectures, and was coming back, and I'd ended my lectures the way I always end my lectures, which is one day in the far future, maybe when all your students, I talk to the students, when you're all esteemed professors, we'll get multi-messenger detection, and we'll be able to do the standard siren stuff, and it's going to be great someday in the far future. And then I get on the plane, and I land, and all this stuff had happened. So, Reed ESIC had sent out, had done this discovery, and he sent out the circular announcing that we have this detection. Had sent me a bunch of emails. A student of mine, Xinyu Chen, they knew I was in Asia, and they're basically, you must be out there grabbing a telescope to point at this thing, because this is the first thing where we have some hope of seeing photons, beyond the gamma rays. And just to emphasize how obvious it all was, it's just, the whole thing was just, we were all kind of in a fog. But it's just, here we are, we're all, everyone was connected. So I immediately connected. The second I touched ground, I turned on my phone, and it blew up. And then, I was on the channel, and we already knew it was at 40 megaparsecs, and that everything was fitting together. Like, everything made sense. And 40 megaparsecs meant, if there was anything like a kilonova, we were definitely going to see it. Like, it just, within a half hour, everyone knew that this was it, what we've been waiting for. Okay. All right. So we sent out the improved sky map, and this is what it looks like. So this is just to give you some sense of how this localization works. So these are the two detector localizations, and they're rings, because it's mostly timing. They're not perfect rings, because we can use the little bit of information, the polarization information, to do a little better. And so you get part of a ring. But when you have three detectors, you do much, much better, especially if you happen to be in this low sensitivity region. And so this is what we ended up with, which is really compact by our standards. And so here's a blow up of these localizations. So this is the light blue is what you end up with, just the two detectors. The darker blue is where you end up doing a bunch of low latency searches. So we're in a hurry. So we have code. I've actually developed some code in the group where we use just the timing and then just the response, because we know the antenna power pattern. And there's some phase stuff we can use. Basically, we use the little information we have. We just immediately estimate sky position. It's very, very fast. We can do it like 30 seconds on a laptop. But it's not doing the full MCMC over all possible sky positions and parameters. And so, but we want to get something out quickly. You get the blue thing. Then when you really do the full MCMC, the full analysis, all possibilities using clean data, you end up with this green thing. Fortunately, they overlap. And you immediately get this 40 megaparsec number. There it is. So we had this all very, very quickly and sent it up. Okay. So by around lunchtime or early afternoon, US time, we had all this stuff was out. Okay. I think I'll spend just a couple minutes on this, just because it's relevant, and this has taken up a lot of my time, which is, for various reasons, I really wanted, I've always been very interested in this multi-messenger aspect. And so to do that, we really needed to find the optical counterpart. The GRB is great, but it doesn't give us a host galaxy. So we really want to be able to find something like a kilonova, anything. If we have matter in the system, there was this thought we should be able to see it. But it's very hard because even in, for example, this case, where we have, it couldn't be better. We have 3 detectors. It's near this sort of spot where where Virgo has no sensitivity. So it's really well localized, 30 square degrees. That's still a huge area of the sky if you're pointing a conventional telescope. So you need a wide field telescope. And at Chicago, we have access to the dark energy camera, which is being used for a dark energy survey. And so we built this collaboration to use this camera to look for counterparts. And it has a 3-degree field of view, so you can just take snapshots and you can tile a fairly wide area. And this really, it's an absolutely perfect instrument in the southern hemisphere to do this. And I mean, you're probably all familiar. HSC, Subaru also has a perfect instrument in the northern hemisphere to do this, even better. And so we've done this a few times. We followed up the black hole triggers. We don't really expect to see anything, but we did it anyway. This is the very first event, 150914. Each of these red things is one pointing of this camera. So it's just we see this big spot on the sky, and we just take lots of images, and we look for things. Okay. All right. So we did the same thing for 170817, and because it was small enough, and because I really wanted to find this thing, so we just hammered away at it. We covered more than the 90% localization region. We actually just covered all around. We went outside the contours, and we kind of dithered because I didn't want any gaps because I didn't want to get unlucky and have it be just in that time. So we just did the best we could. There are some details. Again, there are all these aspects. DCAM, DES, we have this agreement where we trade off with DES, and so we steal their time. And they let us do that, because they're nice and they're also excited about doing this stuff. But that gets complicated. DES just happened to be on the telescope. If this had happened a few weeks earlier, they were not, and we wouldn't have been able to do this at all. Also, this was setting. So this was far in the west. We could only see it right after twilight. 2 hours after twilight, it's gone. Okay, so, and in fact, a couple weeks later, it was gone. And it's been gone until right around now. It's been behind the sun. No one can see it. So, if it had happened a little later, we would have been totally out of luck, the entire community. It had to happen then. So we covered this. We got reasonably deep. And we got an email. I apologize. But this was, we started scanning things by eye because we were very excited because we all knew this was it. And just blinking images, Ryan Chornock found this. Which was, I mean, that morning getting off the plane had been one of the most exciting moments of my career. And then, getting this email was another highlight. Pardon?
When were the 2 images taken?
Well, so this one is a Panstarrs image from a few weeks prior. And this image was taken, I think it was about 11 hours after the event itself. And we had it like that. We knew this was it. And then there's a long, complicated story because other Ryan Foley, who's in our team, then immediately let us know that he had also found it independently because he had a separate program, and then a lot of people found it, and it was amazing. And so here it is. It's just it's a spot, but we got it, and then there was a lot of data, and then it just faded. I might have a little movie later just showing it fading, and then 2 weeks later there's nothing there anymore. Okay, so the short version is that we found it. It's really gorgeous. Okay, so here's kind of a summary of some of the things that were done. I just want to flash this up. I don't want to go in, but this is the curves here are sort of a fairly generic kilonova model. So this is this R process nucleosynthesis. You take neutron stars, you rip them apart, and you get a bunch of R process, and then you predict some light curves. And so these were kind of the light curves that we expected. This is kind of what we were looking for, what we tuned our project to find. And here's our data.
The normalization of those curves is
No. So there are a couple of free parameters. It's basically the mass of the material that you throw out and the velocity, and then there's some YE. So there are a few numbers, but it's only a few. And then you're fitting all this data. And I mean, this is pretty good, given none of this. I mean, we've never seen. Okay, we have a very weak evidence for a kilonova, but this is basically the very first time. Okay, and it's a BNS, and the BNS, we had a trigger. The GRB is kind of irrelevant to this process, right? We found this based on the gravitational wave data alone. This object comes up, and it just kind of fits. So this, on its own is just a remarkable story. So okay, just our little DES group, we then triggered every instrument we could, everything, HST, we got X-ray data, radio, everything, and we just blanketed it. And then in a process of a few weeks, we wrote 8 papers and got them published by the announcement. Even just in here, there's an insane amount of science, and this is just the first pass. And here's a little movie. You can kind of see it disappear. Okay, but it's a very bright spot. Brighter than 17th magnitude. We weren't the only ones. A lot of people. Basically, I think essentially any astronomer that had access to a facility in the southern hemisphere pointed. And so this paper is supposed to sort of summarize all the activity. It says thousands of authors. And so, I mean, it gives you some sense. I think it might be the most observed transient. 87A probably was pretty well observed. But over this time scale of a couple of weeks, I think this has a good claim. All right. We were really lucky. It's really loud. It's really close. If it had happened earlier, Virgo wouldn't have been working, and we wouldn't have localized it, and we wouldn't have gotten the EM counterpart. If it had happened just a couple weeks later, LIGO would have been off. It would have been behind the sun. Yeah, I mean, it's just we're really lucky. I don't know how to turn this into cash, but we're really lucky. It's remarkable. Okay, so I just want to spend. I only have a few more minutes. I just want to focus on one thing I haven't really talked about, but it's kind of the thing I'm most excited about. So I'm gonna, since I have a captive audience, I'm gonna spend some time on this just to close out. So which is the whole standard siren business. So one thing that we get to do here is measure distances. And this really is very different from anything else. I mean, this is really a unique measurement that's only enabled because of this discovery, of this multi-messenger discovery. And it's a pretty simple idea. The point here is that general relativity essentially just tells you what this chirp should look like and how loud it should be. So you can use that theory to just tell you the amplitude, and which means that you can directly infer distance, essentially doing the inverse square law. So you have a direct measurement of distance. There's no distance ladder. There's no complications. Nothing has to be done. Just the gravitational wave data alone. You have a detection of a compact binary coalescence, and you know the distance to it. Okay, but you don't get the redshift, so you need an electromagnetic counterpart, which is why the whole multi-messenger thing is kind of important for this. If you get the electromagnetic counterpart, then you can directly fit for, if it's nearby, the Hubble constant. And so the redshifts gives you the velocity, if you like, the Hubble recession velocity. The distance comes from the gravitational waves. It's a pretty easy equation to solve, and you get the Hubble constant. And just, it should be pointed out that Bernie Schutz was the first to say this. He pointed this out in 1986, that you could do this if you had sufficient numbers of binaries. And he sort of proposed this statistical argument where you get many of them, and you look at all the galaxies within the localization regime, and then you can kind of converge. And it converges reasonably quickly. And then we made some arguments. Actually, what you really want is an optical counterpart. That's the way to go. And GRBs would be the perfect optical counterpart. So if you got a GRB and managed to find the optical counterpart to the GRB, then you'd be in business. And there's been lots of papers on this, but it's all been hypothetical. And then 170817 comes along. Very high SNR, excellent measurement of distance. And we got the host galaxy. I mean, we had that within DCAM immediately. That first email identified the host galaxy and already had the redshift. And so immediately, within 12 hours, I made a Hubble plot. Like it just was laid out in front of you. And so now it turned out that first plot had some issues because it's so close that peculiar velocities are an issue. And so your redshift measurement. So in all the papers I've written about this, my concern was always, the gravitational wave measurement. How well do you measure distance? My concern was never the EM redshift measurement because that's easy and everyone knows how to do that. And it turns out actually that's one of the major sources of error here because it's so close. So now you have to worry about the large-scale bulk flows. And OK, so we made some estimates of this, incorporated it. You solve this equation, and this is what you get. And I still, I just can't believe this plot exists. So this is just from this one event, the first event ever where we have any hope of making this sort of measurement. This is the measurement we get for H0, marginalized over all the uncertainties. And just to guide your eye, this is what you get from supernovae, this kind of orange band, and this is what you get from CMB, the green band. OK, it's a completely different way to do this. This curve could have been anywhere, anywhere. And it's right there. And, I don't, like it's, I mean, I guess physics works. It's remarkable. Like, I really think it's not appreciated what a miracle this is, that it actually is like this. I mean, the fact that it's right between the two and doesn't, settle the controversy, that's pure luck. It really should be it's statistics. But this is extremely, this is amazing. It's the first event. I have a slide on that. But another thing, just, while I'm at it, one of the major sources of uncertainty on the gravitational wave side is the distance inclination degeneracy, which is just to say, if you're face on, you're sort of louder in gravitational waves, so you can be farther away. If you're edge on, you're softer and you're closer. And so we don't know where we are in that. And so that's kind of captured in this, where as a function of the cosine of the inclination angle, the viewing angle, you can see how our measurements of H0 relate. It would help, but it's not enough to do a very clean measurement of inclination. It's very hard to break the inclination, the distance inclination. But it definitely helps. Yeah, but then you have to marginalize over a bunch of other uncertainties in your masses and spins, and you can kind of absorb it in other ways. So it's very hard to break it completely cleanly. But we get some information, and this is you can think of it as this is part of the information. I mean, there's some other plots. I think we have one in this paper where we kind of show how the inclinations change. Now, one thing you could, so there are two ways to do this. One is to say, if you give me your favorite value of the Hubble constant, I can now tell you the inclination of this binary, which is very interesting for the GRB community. Right? Or if you trust your GRB modelers, not saying that compact object modelers, there's anything wrong with them, but if you trust them, then you could have a prior here. Say, for example, from the data, what was the delay in the radio or X-ray? That gives you some constraints within some models for what the inclination could be. Then you get to go this way, and you get to do a better job on H0. Okay. So I'm a little hesitant to play that game, because what's beautiful about this plot is that this has no distance ladder, no astrophysics. It's really clean. OK, there's the peculiar velocity stuff, but it's really very, very clean. The second you start using GRB constraints to impact, it gets a little messier. It starts to look like all the other distance probes. But you can do that, and people have. And the inclination ends up being around here somewhere, 0.8, 0.9. and you end up preferring, if you play that game, higher values of H naught for what it's worth. Okay.
What if the gravitational wave observations gives you the limits on the inclination?
So, right. So it's related to sky position, okay, which in this case we get to fix, which helps a lot. And then it's some relation of what you need to do is you have to figure out the masses and the spins, and then that gives you the full evolution of the waveform, including the amplitude, and then you can kind of break that. Does that make sense? So what we do is we use all the data, we do the full fit, and then you get to marginalize over uncertainty in masses and spins, and that gives you an inclination measurement.
So the low, I mean, the right-hand side is excluded just from that fit.
Yeah, that's right. That's right. So, yeah, that's right. I mean, it ends up, and it's actually,
There's no other priors.
that's right. And what's interesting here, so there is something, that is interesting in the way this relates, is that because it's this, it really has to do with the degeneracy with inclination. It goes, you can't be, sort of more inclined than face on or more inclined than edge on, right? There are these clear, edges, which means that the actual distributions are non-Gaussian, which you can see here. There's this tail. Okay, and this, so this tail is the tail to more, to more edge on and closer, higher H naught. Okay, and so now that flips. If you just have a random population, you get some which have the tails going the other way. So which relates to this question of how does it converge? So you could do the very naive root n, and you'd do OK. But actually, because it's non-Gaussian, it converges faster. And because it kind of flips this non-Gaussianity, it converges even faster. So as a general population, it does better than root n. I mean, it's not dramatic, but it's definitely better.
If the two detectors were twisted relative to each other, you could tell about the circular linear polarity.
Right. So that was the question with Virgo. That's right. So in principle, if Virgo had equivalent sensitivity, and you get high signal to noise in both, you start to be able to play this game. But we're a ways from that. So when you do the Monte Carlos, okay. So eventually Virgo will be at equivalent sensitivity. That's maybe 2020, 2022, and then we get to really play this game because we have. And eventually we'll also have one in Japan and India, and then this all gets much, much better. And actually, maybe I have. OK, I'm going to show one more slide. I think I'll show this one. OK, just so I'll wrap up soon. OK, so this is just to answer your question. OK, so this is just, how well do we do? What's the error on H naught going forward? So I should say this is not collaboration. Everything else, I was supposed to say this at the beginning. I'm speaking on behalf of the LIGO-Virgo collaboration, except for this, which is not on behalf of the LIGO-Virgo. This is work I've been doing with Xinyu Chen and Maya Fischbach. And we'll post it pretty soon, which is just kind of projecting forward how well we'll do. And it just gives you a sense of how things converge. And it's still work in progress, but it gives you some idea. So this is 10%. This is 1%. And there are two ways to do this. One is the original Bernie Schutz way, where you just do statistics over all the galaxies in your localization region. And that's this solid blue curve. And it takes a while. You can think of this as 2024, maybe. This is 2020 out here. This is in a year. And it takes a while to get down to a few percent if you don't have any counterparts at all. If all your BNSs have counterparts, then you get down to approaching 1% by 2024, a couple of percent in the coming years. Roughly speaking, the rates are pretty uncertain, right? We have one event. We're estimating a rate Poisson statistic. I mean, so who knows? So it could be much better or much worse than this, but it gives you some sense of where we're headed, which is right now we have on the order of a 10% measurement, but it's a very clean measurement. As we get more, that'll start to converge fairly quickly, and then it could get really interesting from a cosmological perspective.
How do you do it without counterpart? How do you know the redshift?
So you can take an extreme case where you don't have a counterpart, but the sky volume, we get localization, and if we have inclination, which we do get, especially when we have more detectors and get more polarization, we can reduce the volume localization to a very small volume. And maybe there's only one galaxy, or maybe there's some small number of galaxies, and then we can just use that. If there's only one galaxy, then we say that's the host, even if there's no transient counterpart. We can say, well, it must have come from that galaxy. And so we get a redshift.
What if it's a much more distant galaxy that you don't see?
So it can't be more distant because we're measuring the distance with the gravitational waves, and you can have sort of a wide prior on H0 to get some estimate. It's a fair point, right? Which is galaxies are in redshift space. We're measuring distant, but with any reasonable prior, you can really reduce that, and then you can do very deep images around that and just completely characterize all the galaxies there. So that's the idea. And even if you only have 10 or 20 galaxies, you can then just do it statistically, and only one of the galaxies corresponds to the right redshift. You do that a few times, you converge pretty quickly. Again, it's very non-Gaussian, so you're really using that non-Gaussianity.
You mentioned here that the rate estimates are very uncertain. Determine that too, of course.
Yes, that's right.
How uncertain is there? Are we speaking of an order of magnitude?
Yeah, so I think the formal rate that we've published so far is 1,000 per year per cubic gigaparsec. But that could be as low as a few hundred and as high as 1,500. So that gives you some sense of the uncertainty. So it's large. I mean, it's not 2 orders of magnitude, and before this, we had no idea. And I will say the rate is, if anything, a little high. It's somewhat surprising from the modeling perspective. But we'll know. So a year from now, we expect to turn back on, and I would say within 6 months or a year of that, we'll have this much better constraint, because then we'll have a lot more sensitivity, at least 50%. Factor of 2 to 3 in rates would be expected. So we'll see. I mean, again, we could have just gotten lucky. As an aside, the fact that this was really loud doesn't impact the rate estimate at all. It's just that we got one. And, we've been operating for a long time and haven't gotten anything, and now we got one. Is it one every 6 months at this sensitivity? We don't know. We don't know how lucky we are. OK. Here's the LIGO group at UChicago. Here is the collaboration. It's a very big collaboration, and I guess I'll just end on this slide, which is, this is pretty amazing. We're now in this era of multi-messenger gravitational wave astronomy, and so right now, thank God, everything's off, so we can all kind of recover. But in about a year, we'll be back on, and we'll see what happens next. I'm sorry for running long.
Yeah, running a little bit late, there were lots of questions. Maybe if there's 1 or 2 very urgent questions. Not very urgent.
Someone going back to do the data, looking at the times of detected gamma rays, particularly short gamma rays.
Yeah.
Looked in the gravitational wave data to see if there's any.
Yeah. So we have an ongoing search where we do that, where we trigger off the gamma rays, GRB detections, and we search. And we do sub-threshold searches. Makes me a little nervous because they happen often enough that eventually we'll find something. But yes, so we do that. And it's very interesting in the context of this, maybe there's this very underluminous population that we've been detecting that are really close. And so trying to get that all straight and figure out how it fits, whether we just got really lucky or whether there's a very large population of underluminous nearby GRBs is something I think a lot of people are thinking about. Yeah.
So this is like long